Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Two-dimensional materials represent an excellent opportunity for technology developments, and these developments rely on accurately knowing their material properties, something that can be difficult to determine because of the low dimensionality. An international collaboration has used a technique that employs a standard transmission electron microscope paired with complex computational data analysis to directly measure the thermal expansion coefficient of monolayer epitaxial tungsten diselenide. Some of the innovation for this work came from team members at Lawrence Berkeley National Laboratory, who pioneered the new technique.
The key was not anything fancy in terms of aberration corrections, which put microscopes into the $5 million range. This was an older microscope. The key was low accelerating voltage, so we weren't burning the material. So they have alignments at 60 kilo electron volts. And then the other key thing here was an invention by Colin Ophis' team of changing the electron probe forming aperture. So these are usually like metal foils with little holes cut in them. What his team did was they used some techniques from the X-ray beamline community.
That was Dr. Michael Pettis, Deputy Group Leader and Staff Scientist at the Centre for Integrated Nanotechnologies at Las Alamos National Laboratory and corresponding author on the study. The research groups at both laboratories specialise in working at the nanoscale. While Lawrence Berkeley National Laboratory focuses on analytical techniques, Dr. Pettis' group is proficient at integrating nanomaterials into electronic devices, which means they're very interested in knowing how 2D materials behave when they get hot. His group were keen to use the newly developed analytical technique to analyse materials that have applications in microelectronics.
What these new advances show is that even without very fancy microscopes, you can get strain resolution. For us, we were at about 1.5 times 10 to the minus 4. You can get that kind of strain resolution. The challenge is really in design of experiments and in conducting the post-processing analysis in a systematic way.
The technique, known as 4D-STEM, uses a patterned electron probe which enables diffraction positions to be accurately mapped in real space. This means that strain can be measured with high sensitivity, allowing the thermal expansion coefficient to be measured directly through use of a heated sample stage. Now, the standard technique for directly measuring the thermal expansion coefficient involves X-ray diffraction, but 2D materials are too thin for this. Indirect measurement can involve using electron energy loss spectroscopy to investigate plasmon resonances, or detecting peak position shifts using Raman spectroscopy. But these indirect measurements lead to discrepancies as large as an order of magnitude. These new results support previous findings where only a small change in the thermal expansion coefficient of this material was seen.
We're really expecting to reproduce the EELS results from Robert Klee, the electron energy loss spectroscopy results that show very, very high thermal expansion. We didn't. We reproduced at a smaller scale and with a direct measurement the results of Evelyn Wang, which were kind of like closer behavior to the bulk material. What surprised us was that probably there's something else going on in the EELS measurements with plasmons. We think there's something there that we didn't see in a direct measurement.
This result and the new technique shows what can be achieved when collaborators from around the world come together. A vital aspect of this work was growth of the tungsten diselenide, carried out by researchers at Seoul National University in the Republic of Korea. The material is used in CMOS transistors and detectors. The polycrystalline material analysed is compatible with existing materials, so the 2D version could be used in integrated nanoelectronics, where it's important that the material doesn't delaminate when it gets hot. The research so far has focused on large temperature changes, going from room temperature to over 500 degrees Celsius, but further work could refine this and eventually lead to high-fidelity measurements using lower temperature changes. This work was published in a recent issue of ACS Nano. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.